So to find the nth power of a complex number, so for example, if you want to do 1 plus I all to the power of 3 or something, there's two ways of doing it, and one is always better than the other. One is to use what you'd probably first think of, just use the binomial expansion. So for example, if you have 1 plus I to the power 3, well, you know that a plus b to the power 3 is a cubed plus 3a squared b plus 3ab squared plus b cubed. You can use that. But in some cases, using the polar form ends up being quicker, as we'll see in this next example. Basically, it's quicker if theta is a known rational fraction of pi. So just to see how that would work. Well, if you take 1 plus I to the power 6, now if you did binomial with that, that would take, well, you've got 7 terms to work out. It's actually much quicker to use the polar form. So if we write 1 plus I in polar form, well, the length of 1 plus I is square root of 1 plus 1, which is square root of 2. And 1 plus I, if you picture it, is pointing in the direction 45 degrees, or pi by 4. So it's root 2 times e to the I pi by 4, all raised to the power 6. That's easy to do. Well, root 2 to the power 6 is the same as 2 cubed, and this to the power 6, that's e to the I pi 6 over 4, or 3 pi by 2. E to the I 3 pi by 2, that's just telling you it's length 1 and pointing in the direction 3 pi by 2, which is directly downwards. So that's this thing here is simply minus I. So we get the answer minus 8I very quickly, much more quickly than if you'd expanded using binomial. But what about if we had 1 plus 2I to the power 6 instead? Well, then using the polar form doesn't help you, because the angle here, well, the simplest way of expressing it is inverse tan of 2. And then if you raise this to the power 6, well, you get this horrible looking expression here, which doesn't tell you much. In that particular case, it would be more sensible to just to get the answer as a real part plus I times the imaginary part, which you get by expanding this. So now you can do question number 2. De Moivre's theorem, hopefully you've heard about. I'm not going to really go into detail about it, just that it's particularly simple to prove using the Euler formula. So de Moivre's theorem basically says this. The uses of it are that you can express multiple angle formulas. So if you want, for example, to know what cos 3 theta is, written as powers of cos and sine theta, then all you do is put n equals 3 into this and take the real part. So then you'll get cos 3 theta, for example, is equal to cos cubed theta. And then the real part would be if we expand this, if this was n equals 3, what do we get? We get cos cubed theta plus cos squared theta times I sine theta times 3, plus 3I squared cos sine squared theta, and then plus I cubed sine cubed theta. So if you take the real part of that, then that's equal to cos 3 theta. So it's a very useful formula. But where does it come from? Well, it's very quick to prove. Put 1.16 in. So yes, we just use Euler's formula in this. Basically, it's this. I mean, you just put r equals 1, and you've got e to the I theta is the same as cos plus I sine theta, and here you've got that's equal to cos n theta plus I. sine n theta. So a key result is that there are n nth roots of z, except if z equals 0. So z is some complex number which is not 0, and we want to find the nth root of z. So how do we do that? So what we do is we write z in polar form, r times e to the I theta, where theta p is the principal value. And then we're always allowed to add 2 pi m, where m is an integer, because all that's saying is really we're adding 360 degrees to the, or 2 pi radians to the angle, to the argument, which we're allowed to do as many times as we like. So we actually do it, well, we've got plus 2 pi m. M can be any integer ranging from 0 up to n minus 1, or strictly any consecutive n integers. So why do we need to do this? Well, basically because when we actually raise it to the power 1 over n, then we're dividing the power by n. Then we do get separate numbers. We do get n separate numbers when we're dividing by n. So the final answer to z to the 1 over n is this. So we take the nth root of the modulus, and we've got e to the I, and then all of these different angles. So all of these angles will be different, as opposed to in here where effectively these are all pointing in the same direction. When we take the nth root, we're dividing by n, so we actually get n different directions. Okay, so that's okay. Why do we stop at? Why do we just choose m to be n consecutive integers, such as 0 to n minus 1? Well, if we then look at m equals n, what would happen? Well, if m equals n, then you see the m and n cancel, and we just get plus 2 pi. So we're back where we started. Okay, I've said in practice it makes sense to choose half of the m to be negative, so the arguments, the roots are already equal to the principal arguments. It's sort of up to you whether you do that. We'll see a bit later in the example whether this example here we'll see that happening. Special case, when z equals 1, we call the roots the nth roots of unity. So unity just means 1. And we tend to denote the nth of roots of unity by the symbol omega sub n. It's not universal, but it's quite common in that notation. So omega sub n is simply e to the I 2 pi divided by n. So obviously e to the I 2 pi is just the number 1. And to get the nth roots, you simply divide that by n. So, well, that's effectively, that's one of the roots. Obviously, we have n roots in total. So what are the other roots? Well, we can get the other roots simply by multiplying the exponent by m. So the nth roots of unity we get by choosing m equals 0 up to n minus 1. And we get these. So what use are these roots of unity? Well, if now z is any non-zero complex number, and we let z0 be its first root, so choosing this way of doing things. Okay, so we're choosing m equals 0 to get the first root. Then you can see from comparing this expression here and this thing here, w n to the power m, basically this is simply the first root times omega sub n to the power n. So we can actually write the nth roots of z simply as the first root, and then the first root multiplied by the first root of unity, then multiplied by the second root and upward all the way up to the n minus 1th root. Sorry, the nth root of unity raised to the power n minus 1. Now, if you remember from what we were saying shortly before, if you multiply a complex number z1 by e to the I theta, then you end up with, you just rotate it by angle theta. So effectively, when we multiply z0 by omega sub n, we're just rotating it by 2 pi over n and not changing its size. So the nth roots of unity are actually end up being vertices on a regular polygon or n-gon, all of which lie on a circle of unit radius with one vertex located at 1, 0. So that's illustrated here. So when you actually take the, for example, when you want to find the 6 roots of z0 to the power 6, then all you do is multiply the first root by the 6th root, and then the 6th root squared, and so on, and you end up with all the roots lie on a regular hexagon. So that's true for any complex number, any non-zero complex number. The vertices of the roots of any non-zero complex number will always lie on the vertices of a regular n-gon. It's also then straightforward to show that if you sum these complex numbers, you get 0. Given proof here, the proof is not terribly important. I'll let you read it if you wish. I was going to argue by symmetry, but if you don't believe by symmetry, then you can look through the proof yourself. Okay, so let's do a quick example. So if we want to find the roots of the equation z cubed plus 1 minus I equals 0, so we rearrange this and get z cubed equals minus 1 plus I, then take the cube root, and we get this. Now minus 1 plus I, obviously that has modulus root 2 again, and we need to work out the argument. So the argument is minus 1 plus I, so it's pointing to the left and upwards, so it's an angle of 3 pi by 4. And then we basically use this formula here, and I'm going to choose m equals minus 1, 0, and 1, just any 3 consecutive integers. It's just slightly more symmetrical if you choose minus 1, 0, 1 instead of 0, 1, 2, but either is still valid. And we just plug the numbers in, and we get these values here. If you were to plot these values, you would see that they lie on a equilateral triangle. Okay, so you now should be able to do homework question number 3.